Okay, so in the last video we discussed that how we are actually building the segment tree, what each node means and what they are saving. Like each node is responsible for some range in the original array, and it saves some kind of aggregate like sum or some other function like XOR or something like that in it. Okay, and now we have also seen that how, like, what are we trying to do when we do the first kind of update query and the second kind of sum query. Okay, so for update, what we were doing was we were going into the through the path to the leaf node which is getting updated, update the value over there, and while tracking back, we are updating the values over there. Don't worry too much about how we will do this in code and all. It seems tough, but it is actually quite easy. Okay. Uh, for the query part, we understood that we had to find out the sum of all the leaf node in some range, but again there are some nodes which are above in the level which can be used directly, because like that would mean we need less number of nodes to actually compute the value, right? Something like that. So this was the idea part, but what are the actual complexities of all these operations that we're doing? Okay, so let's look into the complexity part of the things a bit. Okay, so for update, for update, you basically need to update some particular cell over here in the leaf, right? So that means what are the things, what are the nodes in this segment tree that are going to get affected? These, right? So these are the only nodes that are getting affected. So suppose there were n nodes in n nodes as a leaf, right? There were n elements in the array, right? So there are n nodes in the leaf. So how many nodes in the original segment tree do you think are going to get changed? It's exactly log n, right? Think about this, because this node is actually responsible for the range 0 to n minus 1, right? So this is something, so let's keep it n, like these are like almost something like that. So this will be something like 0 to n by 2. This will be something like n by 4 to n by 2, not exact numbers but something like that. This will be something like n by 4 to n by 4 to the half of this. So this will be something like so this range is about n by 4, so that there will be n by 8 range of each node. So there will be n by 8 added, so that would be 3 n by 8, something like that. And this is the leaf node, right? Something like that will be the ranges for each node. Okay, so as you can see that for each node, the range for it is getting split in half, right? So how much split can you go into? Like, unless you get into one, right? Like these range can break down only if they don't get to one, right? So every time it gets getting halved, almost half. So from n you are going to seal off n by 2, something like that, and you're keeping breaking down into it, right? So how much should be the level of this tree? Like how many nodes can there be till you reach a particular leaf node? Log n, right? Something like log of n, of the order log of n, right? So that many nodes only need to change in the segment tree. So for every update operation of the type 1xv, you just need to update log n number of nodes in the segment tree. Now don't worry about how we will find these nodes and change them in the tree. It's quite simple when we code it. So we will discuss all these details when we see how to implement segment trees. Okay, so that's all about update. So if the height is order login, each of the update will take you order login, right? I hope this is clear. So for the next part, we will see into how the query works. Okay, so this would be on the query part, right? Okay, so for query, let's suppose you have some sort of a range like this. Okay, or let's remove the last element from the range just to make a bit of sense. Okay, so you are taking something like this up to this. Okay, this is the thing that you want to find sum of. Okay, so you can use this node. Since both of these are here, you can use this node. Can you use this node? No, because this node contains this node as well, right, in its aggregate, but we don't want that in our sum, so we can't use this node. So this is not used, so we use this node. Okay, we have to use this node because all these 4 nodes are over in the range. Again, this node can be taken, this node has to be taken, and this node has to be taken. Okay, is this clear? Because sum of values in these node will actually give you the sum of whole range. Is this clear to all? Okay. So now, if that's clear, then we are already done with the complexity of query as well. There is just one nice observation, that these selected nodes, which are like the best nodes that you can select for the range, you can have at most 2 per level. Okay, now why is that? First of all, understand that you kind of have a lot of leaf nodes, something like this, right? Now let's suppose these two had something over here, like in the segment tree. So you remove these and use this, right? So there will be like a continuous sequence of nodes in the upper level, right? Like something like this. And then something, maybe these 2 nodes might merge and you might get something in the upper level, right? So first of all, when you are merging from the lower to up, it's something like you have continuous elements in the particular range. So this was the range in the lowest level. This was the range in the n-1th level. This is the range in the n-2th level, something like that. Okay, so these ranges actually are continuous, right? Like these nodes would have been taken, but there is a better way to take those, right, in the upper level. So now in each level only 2 nodes can be taken. Why? Because suppose you have 3 nodes in a particular level, by pigeonhole principle either of the 2 will get paired up in the upper level. Okay, like there will be 2 nodes which can be paired up in the upper level for sure. So you won't be using those 2 nodes and rather use the node that is 1 level up. So like in this case, these 2 nodes could be paired up, so these were used in this way, right? And we removed this and like took this node, right? So we can have only two nodes which are something like this end nodes over here. These nodes can be something which can live at each level of the node structure. So for each level you can have only 2 nodes, right? So there are only 2 in this lower level, 2 over here, 2 over here, right? At most 2 levels. And how many levels do we have? Order log n, right? So if there are order log n number of levels, in each level you have only 2 nodes at most, so there are only 2 into log n number of nodes that can be, that is like the best case you can take, that will give you the sum of any particular range. Okay, so you can use order log n number of nodes to find out the sum of any range in the segment tree, in the basic array, right? Like base array. From that you can use order log n number of nodes to find out the total sum, right? So this is the total idea of segment tree, that we are getting kind of like an order log n in update as well as order log n in query, right? One more thing, if you have a segment tree, suppose you have a array which has only 3 elements. Okay, so how are we gonna build the segment tree for this? Okay, so it would be something like this. Something, first node is responsible for 0 to 2, so their index 0, 1, 2, right? So let's make it array 0 1 2. So now this can be split into two parts. Let's suppose we split it in so we split it by the exact midpoint, so we can calculate it by 2 plus 1 by 2, that is equal to 1. So we take the mid in the left part, so it would be 0 to 1, and this can be just 2 to 2, right, like something like this. And then this can be further split into 0 to 0 and 1 to 1, right? Now the 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 nice thing about segment tree is that you don't need to have everything in the leaf node, so you can always come up at a node and decide whether you need to take that node or not. So we will discuss that while we are coding things, but the idea is that even if you don't have n nodes, you don't really need to worry about segment tree. You don't need to even append new nodes. You can just create a structure like this, okay? And we all know that, as earlier discussed, if there are n nodes in the leaf, you can have at most 2n minus 1 number of nodes, right, in the total segment tree. So there is like a linear number of conversion. So just as a quick peek, you can think about coding this in a way that, okay, so say we convert this tree into an array, okay? So we mark each node with the index in the array, okay? So let's suppose this is 1, okay? So this is 2 and this is 3. So for a particular node which is marked I, its left child is 2 into I and the right child will be 2 into I plus 1, okay? So this is 2, so this child will be 4 and this will be 5, right? Hope this is clear. So in this way, whatever aggregate you wanted to store over here, you can store at this index in the array, right? Something like that. So this will be what we would be implementing in the coding section. So just as a quick recap, we have discussed about segment tree. The problem was to update the value in an array and then find the sum of L to R. So for that, we built a segment tree on the array. Okay, so the leaf node has the value. So for update, you change the leaf node and all the nodes that are above it. For query, you take the responsible nodes which best gives you this aggregate with minimum number of nodes taken. Like you try to take minimum number of nodes and still find the aggregate, right? That's our target. So whichever nodes qualify for that, to take those. For update, you change only these nodes, and there can be height. So whatever the height is, there can be that many nodes only. So, and the height of the segment tree is order log n because we are splitting in half every time. So the time taken for update is order log n. For query, in each level you can have at most 2 nodes. So it will take order log n again, 2 into log n, something like that. Okay. And while implementing, we don't really need to append it into a perfect 2 to the power n structure. You can even build it something like this because it's like a hypothetical structure. We are not going to build this whole tree, but rather we will be keeping this tree in an array, and every node will be marked uniquely by numbers as positions in the array. And if a node is I, its left child will be 2 into I and right child will be 2 into I. So you can think about this. So if you actually think about this, this is a very nice way to generate trees. Not generate trees, but index trees. Like if this is 1, this will be 2 and this will be 3. So this will be next 2 into 2, 4. This will be 5, 2 into 2, 4 plus 1. This will be 3 into 2, that is 6. This is 7. Then this will get 8, right? 2 into 4. So this is like a nice way to fill on a binary tree. Like you have indexes for every node, every cell in a tree, right? Something like that. So this comes in handy in a lot of tree type problems also, like if you want to linearize the tree. So this idea is called linearizing the tree. So in the next part, we'll be seeing how to code the segment tree. So see you over there.